that way. There we go. So whenever Matt, whenever you're ready and connected to audio, if you want to do the intro, we'll get started.
There you go. Can't hear you, Matt. Can't hear you.
Okay.
There we go.
Now? All right.
Yes, excellent.
Okay, sorry, I had to call in a different way. My Zoom was not updated properly. So, well, thank you, everyone. Sorry for coming in a little bit late to what I think is very important for I guess he will be former postdoc when he becomes a research scientist here at PSI, Jianqing Feng, who has a very impressive track record. And so just to, we don't always meet each other at PSI. And so even though Jianqing has been with us for about 5 years, I'm sure a lot of you haven't met him in person. But he has attended some of the past retreats and such. And to also give context to his history before he came to PSI, it kind of takes a little bit of understanding of the Chinese educational system. So as far as I know, Jianqing is a first generation college student in his family. And then he attended for undergraduate the University of Science and Technology of China, which just to let you know is according to the Nature Index of Scientific Research Output is ranked only behind Harvard, Stanford, MIT, and then his graduate institution, the University of the Chinese Academy of Sciences, where he did his PhD. And so he's very high pedigree from the Chinese educational system before coming to us. And then he worked for the Chinese Academy of Sciences in their lab, building up to some of the radar measurements that were done on the Chang'e 3, 4, and 5 missions. He did a lot of the initial tests and calibrations for that. And so that made him an ideal person to come here when we started working with both the Chinese radar data and the Chang'e microwave radiometry data that he'll talk about today. Since being at PSI, he's had a very successful career, lots of publications about infrared, about GPR, about microwave radiometry. He's now a co-I on the Diviner Lunar radiometer team, which is part of Lunar Reconnaissance Orbiter. He's a collaborator and active member on the Juno science team for the microwave radiometer there. So he's gotten involved in a lot of cool projects on his own. I would say he's one of the world's experts. If you ever want to know about ground penetrating radar on the moon, he's probably one of the top 5 people to ask about that. And he's a very good friend, and he's had a great time here. This is all culminated recently in a new paper that's coming out in Nature in about a month that Jianqing and I co-first authored. So that should be one of the exciting topics I'll talk about today. So thank you for coming and working with me all this time, Jianqing, and I'm pleased to see you moving on to this next stage at PSI.
Okay. So thank you for your introduction. So I have to start now.
Yes.
I think so. Were there any other formalities beforehand, Mark? Or
Nope. Go ahead and proceed.
Okay. All right.
All
Well,
right.
excited to hear you talk.
Okay. Hello, everyone. I'm Jianqing Feng. I am a postdoc working for PSI. I'm applying for the research scientist position today. My seminar topic is Unveiling Lunar's Secret, Advances in Passive Microwave and Ground Penetrating Radar Observations. First, let me briefly introduce my research experience. Before joining PSI, I was an associate research fellow in the National Astronomic Observatories of the Chinese Academy of Sciences, or NAOC. NAOC has the world's largest radio telescope called FAST. Specifically, I work for the Lunar and Planet Exploration Program Ground Application System. It is the ground system and research center for all Chang'e and Jianqing Mars spacecraft. And it is affiliated with NAOC. GRASS is also responsible for the storage of lunar samples from Chang'e 5 mission. I was the head of data processing subsystem. I joined PSI as a postdoctoral researcher in 2018, and have been working with Matt Ziegler. And during this time, I became a member of the LRO Diviner infrared radiometer team and the Juno MWR microwave radiometer team. My first research interest is the lunar microwave thermal emission and subsurface temperature. This is generally based on the data from the microwave radiometers of Chang'e 1 and Chang'e 2 missions and the infrared data from Diviner. MRM has 4 frequencies from 3 gigahertz to 37 gigahertz. These are the lunar daytime brightness temperature detected by Chang'e 2 MRM. Another of my research interest is the lunar subsurface structure. I generally use the GPR data from Chang'e 3, Chang'e 4, and Chang'e 5 missions, or it's called lunar penetrating radar, LPR. These are the pictures of the ground tests of these GPRs. I participated all these ground tests. My third research interest is the dielectric properties of lunar regolith. We can study this using either passive microwave data or GPR data. Based on my research interests, my talk can be split into 2 parts. Now I'm gonna introduce part 1 is passive microwave observation of the moon. This includes my study on the global dielectric loss of the lunar regoliths, subsurface temperature in the lunar polar region, and identification of high heat flux regions on the moon. Diviner has detected the global subsurface temperature of the moon, while the MRM derived the regolith temperature in microwave band. If we compare them, we can see that they are quite similar. But except for some Mare region in the near side. Diviner temperature has been used to derive the rock abundance, regulates thermal inertia and locations and temperatures of volatile cold troughs. So we may wonder what we can learn from lunar brightness temperature. So according to the radiative transfer model, a microwave brightness temperature is an integral of thermal radiation emitted from regolith over a certain depth. In simpler terms, brightness temperature is the product of temperature profile and the weighting function WZ. Take the MRIM frequencies for example. High frequencies has a narrow weighting function, so its thermal radiation comes from shallow regolith. Therefore, its brightness temperature has a large diurnal amplitude. Low frequency, such as 3 GHz, has a broad weighting function, so its thermal radiation mostly comes from deeper regolith. And the dB 3 GHz does not change a lot through the lunar day. The weighting function of each layer is determined by density, frequency, and dielectric properties include permittivity and loss tangent. Therefore, the lunar regoliths emit microwave radiation depending on the wavelengths, physical temperatures, and dielectric properties of the regolith. So we can sense temperature, density, and composition of the regolith both near the surface and far deeper. For the same frequency, when the lunar regolith has higher dielectric loss, the microwave radiation signal only goes a short distance into the surface, causing a large amplitude of brightness temperature. On the other hand, when there is low dielectric loss, the signal penetrates deeper, leading to smaller fluctuations in brightness temperature. Based on these features, if we know the temperature profile, we can use the model to feed the TB amplitude to derive the dielectric loss of lunar regolith. So the lunar surface temperature is well constrained by Diviner data, while the Apollo heat flow experiment offers a reliable measurement of the temperature below the surface. With this constraint, we can use a one-dimensional thermal model to simulate the typical temperature profiles across different locations on the moon. Also, we can derive the diurnal amplitude of the brightness temperature of the moon at 4 frequencies. As mentioned before, the high dielectric loss goes shallower, causing a large amplitude, TB amplitude, while lower loss goes deeper, leading to a smaller TB amplitude. So this amplitude map tells us the relative levels of dielectric loss throughout the moon. Based on the temperature profiles constrained by Diviner and Apollo, we use a radioactive transfer model to fit the amplitude of brightness temperature to obtain accurate loss values. Here are the some examples of the data versus models different latitude. And these are the global data and model simulation during the lunar noon. Based on this, we can derive the dielectric loss of the lunar regoliths across the entire lunar surface. The dielectric loss of lunar regolith is closely related to its mineral composition. We can observe a strong similarity between dielectric loss and the description of lunar titanium abundance, but not with the iron abundance. The TB amplitude different wavelengths is also positively correlated with the titanium content. This is because ilmenite has a strong ability to absorb microwave radiation, and titanium exists in the form of ilmenite on the moon. Based on these findings, we have proposed a new relationship formula between dielectric loss and ilmenite content. We claim the loss engines its functional density, frequency, and titanium, but not iron. This formula not only enhance our understandings of dielectric properties of lunar regolith, but also provide possibilities for future microwave-based detection of ilmenite. As low frequency has a broader weighting function, we can use it to figure out the thermal gradient, especially in the polar region. According to the thermal models at very low temperature, the radioactive component in the thermal conductivity becomes negligible. The mean temperature from the top to the bottom of the regolith is almost linear. So we can assume the mean temperature profile Tz equals mean surface temperature Ts plus thermal gradient times depth. And then we know the temperature profile times weighting function is brightness temperature. So therefore, the thermal gradient can be calculated from the mean brightness temperature and the mean surface temperature once we know the weighting function. So here we use the 3 gigahertz TB to retrieve the thermal gradient in the polar region. Here are the data we use. Left side is the mean surface temperature of lunar South Polar region, about 80 degrees. It's an average of Diviner data over 10 years observations. Right side is a scatter plot of MRM measurement of 3 gigahertz. We can see the microwave map is much blurrier than Diviner infrared map because it has a much lower spatial resolution. Now we resampled both dataset into the same resolution. We binned all the MRM 3 gigahertz data point into a map with a resolution of 3 kilometers. The temperature map from Diviner is resampled into 3 kilometers per pixel, and it's also smoothed by a 2-dimensional Gaussian filter to simulate the convolution effect in the microwave observation. Here we assume all the regoliths in the polar region have the same density structure with H parameter of 7 centimeters. Then we use a standard weighting function to compute the gradient across the polar region. So here is the result. More precisely, it is a relative thermal gradient map, because there is a 3 gigahertz. There is a calibration issue for its absolute value. But at least we believe the relative difference from place to place is reliable. The thermal gradient is highly ununiform, and decrease with the increasing surface temperature. The gradient in the PSRs is about 20 Kelvin per meter, larger than non-PSRs. This is beyond our expectations. These are 2 possible reasons. One is the density profile is not uniform across the polar region. PSRs have higher porosity than non-PSRs. Another reason maybe the thermal conductivity in the PSRs are much smaller than that in the non-PSRs. We compare 2 thermal conductivity theories here. One is the conventional model from Pao-Hen 2017 paper. It does not change when the temperature smaller than 100 Kelvin. The other one is recent measurement from Wood-Robinson. It has a temperature dependence and decreases a lot when the temperature gets colder. So we select 2 locations and use high frequency data to test our guess. Location 1 is a non-PSR area with a flat topography. The thermal cycling of this site is the result of diurnal variations superposed on a seasonal fluctuation. Its mean temperature is around 100 Kelvin. Location 2 is a PSR in the center of Shoemaker crater. Its average temperature is around 40 Kelvin. These 2 locations are both observed by Diviner and MRM in 2011. Location 1, we modeled 2-year series of surface temperature and brine temperature at high frequency. Excuse me. The model feeds the data well if we use thermal conductivity from Paul. This is consistent with our result that outside the PSR, the thermal gradient is small and it's under 5 Kelvin per meter. We also found a H parameter of 20 centimeters is needed in the model. At location 2, we did the same modeling with the same thermal conductivity model from Paul. Here we tried 2 different H parameters, 20 centimeter and infinity. Infinity means the density is 1100 kilogram per cubic meter from the top to the bottom. You can see the surface temperature. A model is generally match the Diviner data. However, the TV models are much lower than MRI measurement. The model with infinity H parameter had the smallest density, but it seems its temperature gradient is still not large enough. So an alternative thermal conductivity model theory may be needed to explain this mismatch. here we tried with Robinson's thermal conductivity. It's much smaller than Paul's, temperature below 100 Kelvin, and could create a much larger thermal gradient. The results showed in the PSR of Shoemaker. With the new thermal conductivity, the model fit both surface temperature and microwave TB. Besides, H parameter of 40 centimeter is needed. So generally, our results show the regolith in the non-PSRs has thermal gradient thermal conductivity similar to equator, but with a but in the PSR, a much lower conductivity and a much larger H parameter are both needed to explain the high thermal gradient derived from microwave data. In the region outside the polar region, when we observe different temperatures with the same surface temperature, same amplitude, and the same dielectric loss, is likely due to variations in thermal gradient, or more precisely, it may be differences in heat flux. So just as the Matt mentioned, our recent study is on the competent publish. This region is located on the far side, has high concentration of radioactive element thorium. Normally, areas rich in thorium found near the volcanic regions of the lunar near side. So this region makes up this quite interesting because it has various hypotheses regarding its origin, but all lacks of concrete evidence. However, by analyzing the microwave data, we made an exciting discovery. The brightness temperature of 3 GHz in the computer region are significantly higher than those in the surrounding areas. When examining optical image slope, rock content, and soil density, there is no apparent difference between the competent region and its surrounding areas. The titanium, the ilmenite content is normal. It suggests that the level of dielectric loss in this region is also normal. Additionally, both the surface temperature from Diviner and our temperature model at Compton published show no significant difference compared to the surrounding regions. However, we can see a large hotspot is present in the Compton population in channel 2 microwave data. At 3 GHz, its brightness temperature is higher than any other location on the map, including those equator-facing slopes and crater walls. As we move to the high frequency, the temperature anomaly gradually diminishes, and these features is more evident on the latitude corrected map By contrast, our microwave model do not show any evidence of this thermal anomaly. So despite the higher orbit altitude and lower spatial resolution of Chang-1 microwave radiometer, we also observed the hotspot in the Compton box, which is still very clear, and it shows a trend that the difference decrease with the increasing frequency. So these are the result. We use the data minus model. 3 gigahertz, the difference is around 10 Kelvin. At higher frequency, the difference becomes smaller. However, considering the channel 2 MRM has a resolution of 17 kilometers to 25 kilometers, and the delta TB is the difference convolved with antenna pattern. So we believe the accurate delta TB on the lunar surface may be larger than 25 kelvins. So under normal dielectric laws and topography conditions, we believe that the brightness temperature anomaly in the Compton region is caused by higher internal temperature gradient. Since 3 gigahertz has the largest penetration depths, the brightness temperature difference is most evident at this frequency. So assuming the thermal conductivity remains constant, a higher temperature gradient indicate a strong subsurface heat flow in this area. Based on the microwave model, we can derive the relationship between the heat flux and delta TB. Then use the TB anomalous for frequencies. We can figure out unique heat flux. So how much an increase in geothermal heat flux is required to cause the brightness temperature increase we see? So it turns out we need a heat flux of around 180 milliwatts per square meter to create such a high brightness temperature difference. Considering the lunar geologic environment, we propose the presence of a granitic system enriched with radioactive elements such as thorium beneath the surface of Compton Bockwich with a diameter of 5 kilometers. This is the first time we find granitic system outside the Earth, and this work also represents the first mapping of the lunar thermal gradient from orbit through passive microwave radiometry. This provides a new window into crustal and interior heat-producing structures. So Wolf crater is another interesting region we are working on. We found an evident 3 gigahertz brightness temperature increase near a Wolf crater. The Diviner surface temperature shows no difference compared to the surrounding areas. Wolf crater is not a proven cause area, but with very high silica minerals. We also examined optical images and slopes and rock abundance and lunar soil density. There's no apparent difference, but the brightness temperatures show there is obvious heat anomaly in a large area near Wolf crater. Using the Diviner surface temperature as a constant, we model the brightness temperature of the region near Wolf crater. We don't see the large hotspot features. Using the data minus model, the thermal anomalies become more evident. It has clear boundary, and its extent is huge. It's much larger than Compton Parkwish. And the features become less obvious with the increasing frequencies. So we think Wolf crater also shows high heat flux but it's not under the Caldera rings. Wolf seems to have an offset Pluton system to the northeast. This is same as the Yellowstone. So I'm gonna introduce the ground penetrating radar observation of the moon. This includes my study on the permittivity and dielectric laws estimated from ground penetrating radar and subsurface structure of the moon. Lunar penetrating radar is a type of ultra wideband pulse radar. It works by emitting a high power electromagnetic pulse towards the lunar surface and then receiving the reflections from beneath the lunar surface to detect the subsurface structures. It has two channels. Channel 1 works in the from 20 to 80 megahertz with expected detection depths larger than 100 meters. Channel 2 is from 250 to 750 megahertz with a detection depths over 30 meters. Both Channel 3 and Channel 4 had the LPR on board to explore the geologic structure of the moon. This is the one trace received by the LPR at one location. The horizontal axis is the signal amplitude. The vertical axis is the two-way travel time. If we use a color map to represent the amplitude and put all the traces into one map, we can get a radiogram. After the bandpass filtering, background removal, and amplitude compensation, those data processing depth, you can get a clear radiogram, and we can observe reflections from deeper regolith. Also, we can find some hyperbolas in the radiogram. These are the signal patterns caused by a single target, such as a rock. The propagation geometry of radar signals follows the principle of Pythagorean theorem. The single target in a radiogram is a hyperbola, and the shape of the hyperbola is controlled by the travel speed and depth of the target. This is a simulation of how isolated target imaged using a FTD model. This represents a simulated detection scenario, and the result is the radar images show all the target appears as hyperbolas. We can see as the depth increase, the hyperbolas become more wider. By feeding the hyperbolic curves in the radar images, we can figure out the speed, the travel speed of the radar signals in the regolith. This speed is determined by permittivity, and the permittivity is also is a function of density. So in the end, we can obtain the density of lunar soil. Here are the hyperbolas in the channel 4 and channel 3 radiograms. You can see in channel 4, it's pretty clear. So the velocity results show there is a big difference between channel 3 and channel 4. The permittivity and permittivity and density profile of channel 4 is consistent with Apollo result, but channel 3 has a very low travel speed, but very high density. So it may be caused by the rocks inside the regolith. From the radar equation, we know that the received power and transmitted power is a function of loss tangent and the travel distance. So we can use loss tangent. We can derive loss tangent from the maximum penetration depth and GPR system gain. Here are the result of the loss tangent estimation. We can see the travel depth of channel 4 is much larger than the channel 3. So its dielectric loss is much smaller than channel 3. We also compare the result with Apollo sample measurement. We can see the channel 4 dielectric loss is close to the Apollo 16 and Apollo 15 result, while channel 3 is close to Apollo 11 dielectric loss. And we also compare the result with the dielectric loss derived from a passive microwave. It shows this dielectric loss from GPR matches well with the dielectric loss formula we proposed before, and it's also consistent with the loss from the specific location. After we know the travel speed, we can apply a technique called migration to focus all the hyperbolas into single point. And here is the imaging result of China 2 of the GPR. The results show that lunar soil in the Chang'e 4 landing site is around 40 meters thick and have multiple layers. The top layer should come from the Feng crater. We can see from the optical images. And the other layers maybe comes from the smaller craters, and we observed apparent difference between the first 500 meters and the second, the rest. The first 500 meter radiogram shows more layers, and the top layer is thinner. So we infer that there is a greater impact the old layers, the second layer, and is ejecta create extra layers on top the old layer. So the layering structure is more complicated in the first 500 meters. Our result has published as a cover page article in A&A. So now we discuss the China 1 result. Since the Chang'e 3 mission, there has been a debate regarding the presence of layer structure in China 1 data. So here, my analysis focused on the data obtained from the first channel during the lunar rover's 100 meters, 1,000 meter traverse. When looking at the raw data alone, no structure apparent, because this is because the signal amplitude of the surface direct wave and the antenna ground coupling waves are much larger. It has amplitude of 10 to 4. So this is mask. This masks the signals from deeper reflections. So if you use a smaller dynamic range, we can, to show the radiogram, we can observe more details from deeper regions. The image data can be divided into two sections. In section 1, the noise level is higher than section 2, and the reflections in the section 1 is much flatter than those in section 2, without fewer fluctuations. This is because section 1 has the lower stacking numbers and smaller trace interval. So although these two sections has almost the same trace number, but the rowing distance in section 1 is much shorter. So this is the reason why the reflections in section 1 is much flatter, because it's just a smaller distance. And most of the published results are based on section 1. Here is the data processing pipeline of the China 1 data. We use FIR bandpass filtering and resampling and spreading exponential gain compensation and time correction. Then we got the result. And we can divide the image into 6 units. I think unit A is a blind zone of channel 1 because it appears a lot of perfectly horizontal bands without any fluctuation. And B is a multiple, is a unit with multiple reflections. These reflections are quite parallel to each other. And unit C to unit F, I suspect it's layered stratum. So to verify the reliability of the identifier layers, I compared with ground test data and Jianqing radar images, and also used the error trace amplitude analysis to analyze its noise level. And finally, I use time frequency analysis to analyze the frequency of different travel times. By comparing the raw data images, we discovered that the data features of channel 4 and channel 3 are very similar in the first 1300 nanoseconds with a lot of horizontal bands that show no variation, no fluctuation. However, after 1300, significant difference appears. Channel 4 appears reflective layers with varying depths, while channel 3 still maintains its horizontal band pattern. But for the glacier data, we can see that before 700 nanoseconds had similar features at channel 3 and channel 4, but after that we can see a reflection layer with variation depths appears. So applying the same processing to this data, we observe a distinct boundary between the glacier and the bedrock. And channel 4, the reflections in channel 4, it has a similar characteristic to a glacier boundaries. But channel 3, we don't see similar features. So by taking the average of all traces, and we can derive the average trace amplitude, or ATA. We usually use ATA to analyze its noise level. From ATA, we can see that before 1300 nanoseconds, the channel 3 and channel 4, they have almost identical peaks. These are the horizontal bands in the radiogram, but after 1300 is apparently different. And the channel 3 reached the background noise level of 3000 nanoseconds, while channel 4 both sections reach the noise level around 4600 and to 5000.
Hey, Jianqing, you should think about wrapping it up so that people have an opportunity to ask questions.
Okay. Is this question?
No. You should finish your talk.
Oh,
so that
okay.
we'll have a chance.
Okay.
to
Yeah. So, okay, I have to accelerate. All right. So this shows that at least in the 3000 and to 5000 nanoseconds, the signals is not from the background noise. Okay, this is a time frequency analysis. So you can see a difference channel 4 and channel 3. Channel 4 reaches noise level at 400 nanoseconds. We also compare the reflection at 3700 nanoseconds. This is a layer caused a lot of debate in the previous research. We suggest that these layers is a artificial layers. It's not real in the channel 3 because it also appears in glacier data. The channel 4 is, I think it is real because it's after bandpass filtering is also, there is a lot of reflections exist. So this is we show the difference between the channel 3 and channel 4. So now we believe the reflections in the channel 4 real reflections from subsurface structure. Regarding these layers, we believe the shallow layers are the result of multiple volcanic eruptions of basalt. This can be found in the lunar pit and also on the Earth's basalt output. And other layers should represent large-scale subsurface structures. The thickness of layer C and D ranges from 20 to 10 to 20 meters, which can be observed on the crater walls of many impact craters on the moon. For unit E, has a thickness of 50 to 60 meters. Maybe it's a single large eruption of basalt. So these layers also can be originated from the ejecta from nearby large craters like Leibniz and Elder. So here is the stratigraphy of the landing site on 4. We derived from the GPR. Okay, so conclusion, passive microwave is a good tool to study the dielectric laws of lunar regulates lunar subsurface temperature and identify high heat flux regions. While GPR can help us to investigate the moon's subsurface structure and dielectric laws of regulates on landing site. Okay, thank you.
All right, thank you very much, Jianqing. I guess let's open the floor to questions.
Sorry, it's too long.
No problem. No problem.
It's all right. I gave him the advice to just put everything in there. It's my fault. He's done a lot of work.
I have a question. In the ground penetration radar, what is the suppose in the layering suppose you have some voids, empty spaces. If there are any such voids, what is the kind of resolution that you can get?
Let me see which slide are you referring to.
Yeah, so if there are voids, empty spaces,
Oh,
the layering.
voice. Okay, voice. You mean the resolution of if we detect some voice?
Yeah,
we-
yeah.
You want to know the
So
resolution?
what is the spatial resolution that you can, how small voids that you can detect? Is it like 10 centimeter or?
It depends on the frequency. For the high frequency channel, is the resolution is 30 centimeters. It's larger than 30 centimeters.
Oh, 30, okay.
For the low frequency, like low frequency has a resolution of meters, larger than 1 meter, larger than 1 meter.
Okay, okay, thanks.
Any other questions for Jianqing? I have a question, Johnny. So I like your comparison with the the ground penetration in the craters, and so that's so that gives you an indication of what you're actually seeing on the moon is the layered things that you see in the there we go. It really corresponds to the layering within those craters.
Yeah, we guess these multiple reflections is resulted from those multiple layers. Is represent a multiple basalt eruption during this maybe a very short period.
So can you distinguish between a deposit made by lava flow versus a ejecta emplacement?
No, actually we don't know. But I just I inferred from their thickness because let me see here.
But there's no apparent difference from the loss, where you have a loss from a potentially ilmenite-rich lava flow versus a rocky layer from a ejecta.
You don't see like a density difference or
actually I don't have a very reliable method to calculate the loss of these layers.
Okay.
And so I don't know, but we can give some information from their thickness, because we know the diameter of the large craters near the landing site and their age. We know the age. So only several large craters can deliver ejecta to the landing site, and their thickness, there is a model to constrain their ejecta thickness. So we infer that maybe the Leibniz crater will contribute to layer F because its ejecta is larger than 100 meters. So it couldn't be those smaller layers. And outer is a smaller crater, is ejecta is 20 meters. So maybe it's either unit C or unit D. This is our speculation.
So Jianqing, it's a big institute. People study all different bodies. I was wondering if you could kind of explain what would be interesting if you could get the same microwave measurements from Mars or from icy bodies. That might be a neat topic to briefly discuss.
Yeah.
So like what would be something like if we could measure like the ilmenite on Mars, we don't have a map because of the dust layer. Is that something that you could image lava flows that we normally are covered by a dust layer on Mars, but we can't see them otherwise?
Yeah, if you want, you can use some passive microwave to maybe if your radiometer can send to the Mars.
Yeah, or what might it tell about ice on Mars?
Yeah, ice.
Distinguish between like lava flows and sedimentary layers.
You mean that you using GPR or?
Yeah. Since
Or passive, yeah. Either if you had an orbital GPR or a passive, in the kind of same frequency range as Chang'e 1 and 2.
Yeah, there is a GPR on Mars, on the MRO, right? And it's called Mars. I think they can identify the ice layer from the reflections. Because
There's two orbiters, orbital sounding radars around Mars. It's Marsis, which is on Mars Express, and Sherrod, which is on
yeah, Sherrod. Yeah.
Then there's also a ground-based GPR on Perseverance, which is Brimfax.
Yeah. So
Yeah, so I guess what I'm wondering is that if you had a passive measurement, a passive instrument like this, what could you add to those? And then if you had a higher frequency than the Marsis or Sherrod radars, what might you be able to learn?
yeah, if you have a higher frequency, yeah, it can detect the shallow properties of the Martian soil. So maybe we can figure out the titanium abundance and ice in the shallow soil. I don't know.
Okay.
Well, any other questions? Thank you very much, Jianqing. Appreciate your talk. Very, very interesting. It's always good to see something different, like the ground penetrating radar stuff. So thank you very much.
Okay, thank you. Thank you, everyone.
All right, thank you, Jianqing.